Assalamualaikum and good morning, everyone. This is my lecture number 5 for CHM 577, and today we are going to talk about Lewis structures. Sometimes they're called Lewis electron-dot structures, and then we will use information from the Lewis structure to apply it using the valence shell electron pair repulsion theory to determine the geometry of molecules. This lecture notes or slides were prepared by Dr. Amalina, and I am presenting it for my group. As an outline, at the end of this lecture, you're going to be able to draw the Lewis electron-dot structures for molecules and predict the shape or geometry of molecules based on VSEPR, valence shell electron pair repulsion theory. As you already encounter, valence electrons are electrons that are located at the outermost shell of an atom. Valence means outside, yeah, the outermost. The valence electrons are electrons that participate in bonding. So no inner electrons will participate in bonding, and those that becomes involved in any chemical bonding will only be the valence electrons. So this already have been explained to you earlier, that in group 1A, the electron configuration is NS1, and obviously there is only one electron in the valence shell. For group 2A, it is NS2, where N is actually the quantum number. So S2 means there are two S electrons or two electrons in the S orbitals, and the number of valence electrons is 2. Going on to 3, you have valence electrons of 3 because the electron configuration is NS2 and P1, so S2P1. Giving you 3 valence electrons. Next, the fourth group, S2P2, 4 valence electrons, 4 valence electrons. For group number 5, you have 5 valence electrons because the electron configuration obviously is S2P3. 6, group 6A, you have 6 electrons in the outer shell with S2P4, whereas group 7, which are the halogens, is S2P5, giving you a number of valence electrons of 7. So it's really very easy to remember. Those elements in the group 1 will have 1, go on and so forth. You have until 7, you have 7 valence electrons. So that's pretty easy to remember. So if you look at the this diagram where the valence electrons are presented as dots for each of the elements in this periodic table, you're going to see that all those located in the group 1 have 1 valence electrons, and those in group 7 have 7. For example, there are fluorine, 2, 2, 2, and 1. So that is 7. Chlorine, 7, all the way until astatine. And this is how we determine the number of valence electrons in the periodic, in each element, yeah? Right, moving on to the next slide. So if we are going to make lithium and fluorine react with one another, it really is very simple for you to see where electrons are originated from and where they go upon bonding with one another. So for lithium, you have 1 valence electrons there because the electron configuration for lithium is 1s2, 2s1. The 1s2, they are inner electrons, so they're not participating in any bonding whatsoever. So it's only the valence electrons, the 2s1, that is participating in bonding. Looking at fluorine, on the other hand, you have 7 valence electrons. You can see 7 dots around the F there. And the 1s2, it is the inner, those are the inner electrons. The 2s2, 2p5 are the valence electrons. So when lithium and fluorine combine, these outer electrons of the lithium will be totally transferred to fluorine. Do you remember Pauling's electronegativity scale? The value falls above 2. The difference between the Pauling value of lithium and fluorine is above 2, so you know it is ionic bond. In ionic bond, you have a complete transfer of electrons from the metal to the non-metal. So you have lithium plus and fluorine minus, or we call it fluoride. After it becomes an ion, it becomes fluoride. So it's lithium fluoride, and the lithium electron configuration is 1s2 that I color red, and the fluoride electron configuration is 2s2, 2p6. It becomes 2p6 because the valence electrons of lithium come and join the 2p5 of your fluorine. So you have practically lithium having the electron configuration of helium, which is a noble gas, whereas fluoride has an electron configuration of neon, which is another noble gas. So that is actually the absolute aim of each element that bonded with each other, is to have electron configuration of the closest noble gases. So if you break down the reaction, you're going to see that lithium just now loses an electron to make lithium plus. The electron is taken up by the fluorine atom to make fluoride. So lithium plus fluoride makes a salt, which is lithium fluoride. So this is down here is the Lewis diagram of lithium fluoride. You have the dots of the electrons around fluorine or fluoride are represented by dots there. Some textbook will actually make the lithium maybe a cross, and the electrons belonging to fluoride to be dots. So you can distinguish that the cross electron has joined in the dots electrons to make your lithium fluoride. So that's why sometimes it is also called electron-dot structure, cross and dot. So that is about ionic bonds. So what about covalent bond? We all know that formation of covalent bond does not occur with a complete transfer of electrons from one atom to another. Instead, covalent bond is formed when there is a shared pair of electrons between two atoms. An example is when you have two fluorine. Remember, covalent bond is formed when the Pauling's value of the elements combining less than 0.5. The difference between the Pauling's electronegativity value is less than 0.5, then you're going to have a covalent bond. So practically, if you are matching up, if you are making one fluorine bonding with another fluorine, this will have a difference in Pauling electronegativity value to be exactly 0 because they are the same atoms. So you know that the bond that's going to be formed is a covalent bond. So a covalent bond is a chemical bond in which 2 or more electrons are shared by 2 atoms. Then why would they share? They share the electrons because they will make both atoms fulfill the octet rule. Yeah, remember octet rule? Octet rule is the rule that says that all atoms will only be stable if they have 8 electrons on the outer shell. So you have fluorine, one fluorine atom on the left with 7 electrons, another fluorine atom on the right with another 7 electrons. And the way to make both the fluorine atoms fulfill the octet rule is to make them share a pair of electrons. So if they share a pair of electrons in this way, the electron that is shaded yellow in this diagram, 8 electrons belonging to the fluorine on the left, and then go to the fluorine on the right. It also has 7 plus 2, 8 electrons. So you're going to have both fluorine atoms fulfilling the octet rule, having the electron configuration of a noble gas. So if you see how this is going to be represented in the oops, excuse me, this is yeah the electron in the middle, the 2 electrons in the middle that are being shared by the 2 fluorine atoms make one single covalent bond. Can you see it there? This is a one single covalent bond that is represented by that electron pair in the middle, because it's being shared by the fluorine on the left and by the fluorine on the right. But the 6 electrons each on each fluorine are what we call lone pair of electrons. That means those pair of electrons are not being shared by any other elements. They are practically existing as lone pair of electrons. So you have 1, 2, and 3. 3 pairs of lone electrons that make up 6 electrons, and we say these are lone pair of electrons. And these lone pairs of electrons, remember them because they are going to be very, very vital when we talk about coordination compounds later on. Yeah. So I hope you understand that by sharing one pair of electrons between the fluorine, they will make a covalent bond between them and fulfill the octet rule to make high stability, to achieve high stability. So that is about covalent. The octet is achieved through sharing of electrons, whereas ionic, in the previous slide, the octet is achieved by complete transfer of electron. Right. Let's have a look at when you have two different atoms of two different types, for example, hydrogen and oxygen. How are they going to react to make sure that each one of those atoms complete the octet? Yeah, but remember, the octet for hydrogen is not 8. The octet for hydrogen is 2 because it is in the first shell. It doesn't have orbitals, it only has s. So 2 is good enough for hydrogen. So if you have, for example, hydrogen, you want to make it bond with oxygen. As you can see, oxygen has 6 electrons, 6 valence electrons. How do we know that? Obviously, because, have a look, oxygen is seated on the group number 6. Group number 6 means it has 6 valence electrons. Go back to this one. Now, 6 valence electrons, it is going to need 2 more electrons to meet octet or to make the complete octet. So the 2 more electrons will have to come not from one hydrogen but from 2 hydrogen atoms. So one oxygen will require 2 hydrogen atoms to make a molecule that satisfy the octet of all the atoms involved. So water, H2O. So you have here the hydrogen on the left shares its electron with the oxygen to make a covalent bond, and hydrogen on the right also shares its single electron with oxygen to make another covalent bond. So you have in water oxygen bonded to two hydrogens making two covalent bonds, and you will see that there are one lone pair of electrons at the bottom and another lone pair of electrons at the top. So you have two single covalent bonds and two lone pairs of electrons. Yeah. So that is about water. And that is forming a single bond for water is enough to complete the octet. What about when we do not complete the octet by just formation of a single bond? So you need to do something else. So one example which you see having double bond to complete the octet is carbon dioxide. I'm going to go through that with you in a while. And triple bond is represented by a nitrogen molecule, nitrogen gas molecule, where it needs to make a triple bond between the two nitrogen to complete the octet. So what's the story about the double bond? What's the story about the triple bond? I'm going to go through those a little bit later when we go into how to determine or how to draw the Lewis structure for each molecule. Just bear that in mind. I'm going to go back to that one later. Now, when we look at the covalent bond, everybody knows that covalent bond is extremely strong. However, a single bond is, even though it is strong, a double bond of the same atoms will be stronger. A triple bond even more so. Similarly, if you have hydrogen here, I'm going to show you this diagram here. When you have hydrogen, one atom of hydrogen bonding with another atom of hydrogen, making a hydrogen H2 gas molecule, you're going to have the distance between the nucleus of the hydrogen on the left with the nucleus of the hydrogen on the right is actually 7.4 picometers. So you're going to see that the bond length of HH is 74 picometers. When you have hydrogen bonded with iodine, we know that iodine is a huge atom compared to hydrogen. So you see this big purple atom on the right and the gray on the left. The separation between the nuclei of hydrogen and iodine is a lot bigger. It is 161 picometers. So we are saying that the bond length of HI is 161 picometers. So based on that determination of bond length, it has been determined before that the CC, carbon to carbon single bond length is 154 picometers. When you have carbon to carbon bonded in a double bond, contohnya, for example, in ethene, you're going to see experimentally that that bond is shorter than a single bond. So double bond is shorter than a single bond. But when you have, for example, ethine, yeah, C triple bond C, that bond is then a lot shorter than the double bond, even more so shorter than the single bond. So this bond length actually will give you some indication of the strength of the bond. The shorter the bond, the stronger it is. The longer the bond, the weaker it is. So you're going to see that triple bond CC is the shortest, the strongest of these three that are shown in this slide. Now, let's have a look at CN, carbon to nitrogen. CC, if you look at the position of carbon and nitrogen, in the periodic table here, carbon is in group 4, whereas nitrogen is in group 5. And we know, going from left to right of the periodic table, the atomic radius decreases. Yeah, so carbon is bigger than nitrogen, and that is reflected in this slide. You can see that C single bond C 154 picometers, but C single bond N is shorter. Why is it shorter? Because nitrogen is smaller than carbon. And it follows that the C double bond N is shorter than C single bond N, whereas C triple bond N is the shortest of the three. So in terms of bond length, triple bond is the shortest, followed by double bond, followed by single bond, and single bond is the biggest. And the strength is reverse. Yeah, the strength of the bond is reverse. So when we compare the general properties of ionic compound versus covalent compound, yeah, if you remember, ionic compounds are formed when there is a complete transfer of electrons from metal to non-metal. You get ions. You get the metal becomes a cation, a positively charged species, and the non-metal becomes anion, a negatively charged species. Whereas covalent compounds, none of the atoms get charges. They are not anions, they're not cations. They simply share the electrons, so nobody loses anything, nobody gains anything, but they just simply share that pair of electrons between them to complete the octet. Now, in terms of appearance, when we compare an example of ionic compound, sodium chloride, compare it with CCl4, tetrachloromethane, yeah, CCl4. In terms of appearance, in room temperature, in room ambient condition, sodium chloride is a white solid. Everybody knows that salt, the table salt, is a white solid, whereas CCl4 is colorless liquid. So that tells us something about the difference between ionic compound and covalent compounds. Ionic compound typically will have a melting point, a higher melting point than covalent compound, a higher boiling point than covalent compound. So melting point of sodium chloride is 801. So at 25 degrees Celsius room temperature, or 30 in Malaysia, or 35, it is still in its solid state. It's not melting. However, for CCl4, being covalent, it has a much lower melting point. It has a melting point of minus 23 degrees Celsius. So minus 23 degrees Celsius is a lot lower than our room temperature. That is why you have CCl4 present in liquid state at ambient conditions. The molar heat of fusion is higher for ionic compound compared to the covalent compound. Molar heat of vaporization definitely higher for ionic compared to covalent. Now the density obviously is higher ionic than covalent. Solubility in water. Now ionic compounds are polar, very, very polar. Yeah, because we see that the sodium becomes sodium plus, chlorine becomes chloride, and positive charge, negative charge, very, very polar. And water is a polar molecule. We all know that water is a polar molecule. How do we know? Because when we look at the difference in Pauling's electronegativity values, you find that the difference is quite high. quite high, but it is still less than 1.6. So water is a polar molecule, and you have ionic compounds. They will definitely be easily soluble in water, because polar and polar, polar solute, polar solvent, the solubility is going to be high. However, when you look at CCl4, CCl4 is a very, very non-polar compound. Even though you have the CCl bonds are polar bonds, yeah, but the dipole moment in the molecules cancel each other. If you still recall, the shape of CCl4 is tetrahedral, and the dipole moment of each bond is acting exactly at the opposite direction of each other, making that the dipole moment of that molecule to be zero. So it is very, very non-polar molecule. That means a non-polar molecule in a polar solvent is not going to mix. They're not going to mix because of the difference in polarity. So very, very low very, very low solubility of CCl4 in water. Obviously, when you have solubility, the electrical conductivity. Now, electrical conductivity usually is high for something that has free ions or free electrons moving in the structure, within the structure. So the electrical conductivity of sodium chloride in solid state obviously is poor. CCl4 being terribly nonpolar will have a very, very poor electrical conductivity, whether in solid or liquid state, unlike your ionic compound. Your ionic compound, when it is in liquid state, when you melt sodium chloride, the ions will exist as free moving species. The sodium plus and the Cl minus will be free to move around, and they will become extremely good electrical conductors. Yeah. So those are the difference in properties of ionic compound versus covalent compound. So all of those differences can be explained through the bonding that exists between them, through the shape of the molecule, and also through the strength of bond that you can find in the compound. Right, this is what I'm talking about. How do you go about writing or drawing the Lewis structures? These are the rules. Very simple rules. There are 4 rules. The first rule, when you are given 2 elements and you are asked to draw the Lewis structure of the molecule that's going to be formed through the combination of those elements, first of all, you must draw the expected skeletal structure of the compound. Yeah, draw the skeleton of that compound first. And if you have 2 different atoms, you choose the least electronegative element in the center. For example, water. You have H and O. So for you to determine to draw the Lewis structure of water, you put the least electronegative element in the center. Well, water probably is not a good example. We take methane. Yeah. Methane, carbon and hydrogen. You have carbon has, higher. Oh, yeah. Put the least. We will go through the example in the next slide. Yep. And number 2, the rule is count the total number of valence electrons for all the atoms involved. Add 1 for each negative charge. You subtract 1 electron for each positive charge. You complete the octet for all atoms except hydrogen. And now this is number 4. This rule number 4 will determine whether you are going to get single bond or double bond or triple bond. Okay? Don't know whether this is going to work. Right, like that. So rule number 4 will actually give you information whether you need to form double bond or triple bond. So let's go through some examples. For example, if you have NF3, nitrogen with 3 fluorine atoms. So step number 1, you determine between nitrogen and fluorine which one is less electronegative. You put that in the center. And we know that fluorine is a very, very electronegative atom. Nitrogen is less electronegative. So you put nitrogen in the center. So you draw N with F, and with another F like that. So that's the skeleton. The dots don't come here yet. Don't come into the picture yet. Step number 2 is you count the valence electrons. Nitrogen has 5 valence electrons, 2s2, 2p3. Fluorine has 7 valence electrons, 2s2, 2p5. So there is 1 nitrogen, 5. And there are 3 fluorine, 3 times 7. So you get 26 valence electrons. Yeah? Remember, you have 26 valence electrons. Step number 3, you draw a single bond between nitrogen to fluorine. Yep. Right, first of all, like that. I'm going to, yeah. Okay, just like that. Step number 1, you just draw this skeleton, N with F, 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 right? And step number 2, you count the valence electrons, you get 26. And step number 3, you draw the bond between the nitrogen and the fluorine accordingly, like that. So you get that structure. And then you complete the octet on nitrogen and fluorine. We all know that each one of this bond represents 2 electrons. So you're going to be needing for fluorine 6 more. This fluorine also going to require 6 more electrons because 2 is already in the bond. And the fluorine on the right also will require 6 more electrons. So all you have to do is take 6 electrons each for each of your fluorine like that. And your nitrogen in the middle has 1, 2, and 3 bonds that represent 6 electrons. So you need to put 2 more electrons at the top, right? So you just draw. Don't count it yet. Don't count those electrons yet. You just draw to ensure that the octet of each atom is completed, right? And step number 4, you have to check whether the number of electrons in the structure is equal to the number of valence electrons that you count here at the top, 26 electrons. So if you count each one of these electrons and they become the same as the total number of valence electrons, then you already get the correct Lewis structure of that molecule. So let's count together. The dots are 6 on each fluorine. So 6 times 3, that's 18, plus 2, that is 20. 20 plus 1 bond, 2 bond, 3 bonds, 6. So 20 plus 6, you get 26. So voila, that's a happy story. You get 26 valence electrons as you counted in step 2, and you also count physically that you have drawn 26 electrons. So that's fine. Everything is good and happy. Now let's have a look at the second example. Now the second example is a carbonate anion, CO3 2 minus. Now as ever, as usual, let me see whether I can do this. Yep. I'm going to take apart all this calculation. Oops. Take that apart. First step. C is less electronegative than oxygen, so C is put in the center. You have 1 carbon and 3 oxygen, so you just draw the skeleton COOO. That's simple enough. Step number 2, you count the valence electrons. There are 4 for carbon, 6 for each one of the oxygen, and -2 for the charge of that anion. So you have 4 plus 3 times 6 plus 2. So you should have 24 valence electrons. So put that at the back of your mind for now. Step number 3, draw the single bond between each one of the carbon to oxygen, like so. So you draw that bond like that. Yeah, that's step number 3. And then complete the octet on the carbon and oxygen. So oxygen on the left is going to require 6. 1 on the bottom, 6. 1 on the right is 6. Your carbon is going to require 2 more to complete the octet. So let's do that. So at this stage, you need to pause and check. You need to check one more time. How many electrons do you have already in the structure that you draw? So you have the dots are 6 plus 6 plus 6 plus 2, that's 20, right? And then you have um, 6 electrons for the bonds, 2, 2, 2, so 26. So you are saying that you get 26 electrons, which will be a little bit more puzzling for you because you shouldn't have this many electrons. You should only have 24 valence electrons. So what are you going to do? Step number 5. Remember this rule that I was telling you about. Where is that rule? At the top. Oops, excuse me. Yeah. Now, this rule. If the structure contains too many electrons, as in the case of the CO2 2- that you draw, you need to form double and triple bonds. You need to form double and triple bonds by collapsing. Let me write that. By collapsing a pair of electrons. So what do I mean by collapsing pair or pairs of electrons? Let me show you how. Yep. How is that done? Oops, where is it? That one over there. So you know that there are far too many electrons. You counted 26, but you need only 24, so you need to do something. So you collapse that electron at the top. Yep. And then this one, you collapse it, making a double bond like that. Make a double bond like that. Yeah. You collapse. You take away that electron at the top, those 2 electrons at the top, make a double bond like that. And count the electrons again. So, oops. Yeah. So let me do this. You collapsing 1, 2, 3, and 4. Take them away. 2 from the carbon, 2 from the carbon, 2 from the oxygen, and draw another bond between the two atoms that you have collapsed the pair of electrons, two pairs of electrons, and count. So let's count. You have 1, 2, 3, 4 plus 6, that's 10, plus another 6, that's 16. 16 plus 2 is 18, 20, and a double bond represents 4 electrons, that's 24. So by collapsing two pairs of lone electrons and replacing it with another bond, you are reducing 2 electrons that is in excess. So you have the correct drawing of the Lewis structure to be like this. Between the carbon and one of the oxygens, there is a double bond. Between the carbon and the two other oxygens, there is a single bond. And rechecking the octet, you still find everything is still octet compliant. So this oxygen on the right here has 2 lone pairs of electrons, make 4 electrons, and 2 pairs of electrons in the covalent bond, another 4. So you have 4 plus 4 to be 8. So even after collapsing those lone pairs of electrons and adding another bond between C and O, you still have a complete octet. Carbon also has a complete octet. This oxygen on the right has a complete octet. And of course, the 2 remaining oxygens have been having a complete octet. So this is the correct structure of, or the correct Lewis structure of CO3 2-. I hope you understand that. Remember, when you have far too many electrons, you collapse 2 pairs of lone pair and make a single bond additional. Yeah? Collapse 2 lone pairs of electrons, one from one atom, another from another atom, collapse it, remove it, and then add 1 bond additional, make a double bond or probably a triple bond. That is going, if that is still not meeting your number of valence electrons, you need to do it the second time. Yeah, you need to do it the second time. For example, no, I'm not going to give an example now, but you can do a practice exercise on nitrogen N2. Yeah, try to draw the Lewis structure for N2, nitrogen gas. And you're going to end up with the triple bond as I was explaining earlier. We're going to go through that later. Yep. Next. Let's have a look at formaldehyde, CH2O. Yeah, CH2O if you draw the structure, it can make this form of bond, HCOH, you can have that, or you can either have this one, you have CHHO. The skeleton can look like this. Either the carbon takes in 2 hydrogen and 1 oxygen, or you do it linearly like that. So, how do you determine which of the 2 skeletons are more appropriate? So that is what happens when you have to consider formal charges. Yeah. An atom's formal charges is the difference between the number of valence electrons in the isolated atom and the number of electrons assigned to that atom in a Lewis structure. That sounds a little bit more confusing. So just look at it. Formal charge of an atom is in a Lewis structure is equal to the total number of valence electrons in the free atom minus total number of non-bonding electrons minus half a total number of bonding electrons. So that is the formula to determine the formal charge. Total number of valence electrons in the free atom minus total number of non-bonding electrons minus half of the total number of bonding electrons. So the sum of the formal charges in the of the atom in a molecule or ion must be equal to the charge of the molecule or the ion. This is what's important. You must check that the sum of the formal charges of the atoms in a molecule or ion must be equal to the charge of molecule of the ion. So let's have a look in here. So let us check this structure, the HCOH. If you go through the whole of your Lewis structure steps that I showed you earlier, you're going to end up with hydrogen, carbon with a lone pair of electrons, a double bond between the carbon and oxygen, another lone pair on the oxygen and hydrogen. So what you're going to see is that to determine which one of the two structures of formaldehyde, let's have a look at the top here, yeah, either this linear structure or this branch structure, you need to determine the formal charges. So let's go through the calculation of formal charges together. So I call this structure A. Yeah, let's make it into red. It is not in your notes, so you may want to add a few things that I have added in here. So this is your structure A, which is the linear, and that is your structure B, which is the branched. Okay, for structure A, how do we determine the formal charges of the atoms in structure A? First you need to count. Let's have a look. You have carbon and oxygen. You need to determine whether this carbon or that oxygen. So carbon, the formal charge on carbon, first of all, number of valence electrons in the free atom is 4. Yeah. Yeah, number of valence electrons in the free atom is 4. Total number of non-bonding electrons. Now, non-bonding electrons are lone pair of electrons. So if you look into this structure that you have drawn your Lewis structure of, you have on carbon, there are 2 lone pairs, 2 electrons that is in one lone pair. So you have number of non-bonding electrons is 2. So 4 minus 2 minus half of the total number of bonding electrons. So bonding electrons for carbon, you have 1, 2, and 3. 1 on the left and 2 on the right of carbon. So there are 3 bonding electrons. So 3 bonds, that means 6 bonding electrons. So half of total number of bonding electrons is half minus 6. So you're going to get 4 minus 2 minus 3 is equal to minus 1, because 4 minus 2 is 2. 2 minus 3 is minus 1. So the formal charge of your carbon here is minus 1. Let's have a look at the formal charge of the oxygen. So total number of valence electrons in the free atom of oxygen is 6. Total number of non-bonding electrons, a pair of lone electrons there, minus 2, 6 minus 2, and half of the number of bonding electrons. So 2 on the left and 2 on the right, so that's 6 electrons. No, 2 on the left makes 4 electrons, 1 on the right make 1 times 2 electrons, so that's 6 electrons altogether. So minus half times 6. So 6 minus 2 is 4. 4 minus 3 is 1. So your oxygen in this situation has a formal charge of plus 1. So you have for structure A, your carbon having minus 1, whereas your oxygen having plus 1 formal charge. So keep that information first. Let us check structure B. Structure B, if you go through this one here, if you complete the octet, you're going to put 2, 2, 2, that is 6 electrons, and 2 more there. You're going to have too many electrons. You're going to collapse the electrons, and in the end, your Lewis structure that you will come up with for this structure is like this. You can practice your Lewis structure drawing with that one, yeah, but later. This one is the Lewis structure for HC double bond O, if you go through the practice. So let us check this structure, the formal charge of carbon and oxygen in structure B. So in structure B, the formal charge on carbon is 4 minus 0. Why 0? Because there are no non-bonding electrons for your carbon. 4 minus 0 minus half of 4. 1, 2, 3, and 4. Half of 4. Well, the 4 bonds make for 8 electrons. Half of 8. Sorry. Half of 8. This is not 4. Half of 8. Yeah. So 4 minus 0 is 4. Minus 4 is 0. Yeah. So in this situation, your carbon is having a 0 formal charge. What about your oxygen? It is 6. Yep. 6 number of valence electrons in the free atom of oxygen. Minus 4. Why 4? Because you see there are 4 dots there, non-bonding. Minus 4. Minus half of 4 electrons. 1, 2. 1, 2. 3, 4 for the double bond of the oxygen. So half of 4. So 6 minus 4 is 2. 2 minus 2 is 0. So in this situation, you have carbon having formal charge of 0 and your oxygen also having formal charge of 0. So now you have to consider these two situations. Which one is better, structure A or structure B? Now, I'm going to introduce you the concept of formal charges and Lewis structures. For any neutral molecule, a Lewis structure in which there are no formal charges is preferable. When there are no formal charges, that means when 0, for neutral molecule, remember, neutral molecule, you do not want to see any charges. So if you get a structure with give you no formal charge, it is preferable compared to the one which formal charges are present. So that's number 1. Number 2, Lewis structure with a large formal charges are less plausible or less possible compared to those with small formal charges. And number 3, among Lewis structures having similar distribution of formal charges, the most plausible structure is the one in which the negative formal charges are placed on a more electronegative atom. So this is another rule not applicable to your formaldehyde for now. But if you do encounter situation like this, remember that if you have counted the formal charges of the atoms in that structure and you find that the most electronegative atom has the negative formal charge, then that's better. If the reverse, then it is not good. So knowing these 3 rules for between formal charges and Lewis structures, we determine that the most likely structure for formaldehyde, CH2O, is this. Why? Because 1, it is a neutral molecule, so you do not want to see any formal charges. That's already correct. Compared to this one, it does have formal charges. So this linear arrangement is less plausible, less possible compared to this structure B, which is that CHHO. Yeah. So that is how you choose if you find two Lewis structures that are acceptable. Yeah, first you draw the Lewis structures, everything is correct, no problem. But both of them having good match with the number of valence electrons, so you have to determine through formal charges. So that is how you do that. Right. Going on next to resonance structure. A resonance structure is one of two or more Lewis bases for a single molecule that cannot be represented accurately by only one Lewis structure. Now, a classic example of this is ozone. Yeah, ozone. When you draw ozone, the Lewis structure of ozone, you are going to have two possible scenario. One, the double bond on the left, another one, the double bond on the right. So both of them are equally correct. So we say that the two structures are resonance of each other. They resonate. So in situations like this, you're going to find that in that molecule, this double bond and that single bond, one double bond on the left, single bond on the right, and the other one single bond on the left, double bond on the right, when they make a resonance structure, actually they are neither single or double. This will be single bond, 1.5 bond. This will be 1.5 bond. So you're going to see that the two bonds, OO, and another one, OO to the left of ozone, they are actually of the same length. You don't have one shorter, one longer. You have both of the OO bond in ozone to be the same length, but both are longer than a double bond, but shorter than a single bond. So you say that is resonance. Similarly, when we talk about a carbonate anion, CO3 2 minus, the one that we determined a little bit earlier, this one here, we determined it here. We say that this double bond is necessary because it will make the number of valence electrons correct. But what is going to stop you from putting the double bond on the CO that is pointing downwards, or the CO that is pointing to the left? Those will be equally correct. You can put the double bond either on the electron or on the oxygen, carbon oxygen on the right, or the one at the bottom, or the one on the left. So the three possibilities are actually correct. So you can have the C double bond O pointing to the oxygen downwards, or pointing to the oxygen on the left, or pointing to the oxygen on the right. And if the three are equally correct, then you are going to say that these three are resonance structures. So you have this one resonating with the one in the middle and resonating with the one on the right. And as I was explaining to you with the ozone, in actual fact, experimentally, when you do look at this anion through maybe X-ray crystallography, you're going to find that you do not see two long bonds and one short bond. You see three bonds that are equal to one another. All the three will be longer than a double bond, but shorter than, shorter than a single bond. So the resonance structure will actually make these three structures having the same. So it's neither to the bottom, neither to the right, neither to the left. Yeah. So all the three will be the same. And you are going to also have exception to the octet rule. You're going to have an incomplete octet where when you have beryllium BeH2, you have 4 electrons. In that case, that is an exception. They can be stable. This is one exception. And you may also have your boron here, you also incomplete octet, but that is fine. So beryllium here will have only 4 electrons, and your boron here will have only 6 electrons, and these two molecules are stable, so we say that those are exception to the rule. You may also have another type of exception to the rule where you have odd electron molecule. You will find for NO, the nitric oxide molecule, quite stable. You're going to see that your nitrogen here doesn't have 8 electrons. It has 1, 2, on the bonds you have 4, and then plus 3 electrons. You're going to have only 7 electrons for nitrogen, and that is fine. That is the exception. So these are the 3 exceptions so far, and you're going to also see expanded octet where the central atom with the central atom has more than 8. SF6, for example, if you count the electrons on sulfur, you're going to see that it has 1, 2, 3, 4, 5, 6, 12 electrons around it, and that is fine too. It is another exception. We call it expanded octet, and this actually happens principally if the central atom has a quantum number of bigger than 2. That means it is the larger atom. So the larger atoms are able to accommodate more number of other atoms attached to it. So there are 3 types of exception to octet rule. You have incomplete octet. The examples are BeH2, BF3. And the second type is the odd electron molecule, which is your NO2. And the third type is your expanded octet, the example of which is SF6. I think I'm going to stop there. This has been quite a long lecture. This is a 1-hour lecture for now. Please ensure that you understand how to draw Lewis structures. And if you do have questions, please ask me in class or in our Telegram group. So go ahead and understand this. My second lecture from this set of slides is going to be VSEPR. So for now, go ahead and listen to this lecture again and again if you are finding it difficult to understand on the first round. And then the next lecture from this slide will be VSEPR, which is the determination of the shape of molecule based on the valence shell electron pair repulsion theory. So for now, that's all. Thank you very much. I'll see you in lecture number 6, I think. Okay then, bye-bye. Assalamualaikum.